that's my outline. I motivate our work. I'll explain what's a fractal for everybody. I think everybody has at least an idea. And I'll talk about first about mathematical fractals. And then I'm going to talk about fractals that we can find in nature. And in landscapes around us, and also in the human body and animals and everywhere. And I got some conclusion, then that's it. Yeah. In school, we learn about geometrical shapes like squares, cones, spheres, and that's it. But if we stop to think, can we really describe nature with these shapes? Can we find cones and square line in the park or something? I don't think so. We will need some new objects that has some different properties. And that we call a fractal. So, what's a fractal? Let's generalize a bit our notion of dimensions. Like, if we have an object like a line, it could be an object. Let's see how the mass would scale when we rescale it. Let's see how many copies we would have of a line if we double the size of the line. There will be 2 lines, which is 2 to the first power, so the dimension is 1. If we take a square instead and double the size of the square, it will contain 4 copies of the original square, which is 2 to the second power, so the dimension is 2. And if we get a cube and double the size of the cube, we'd have 8 copies of the cube, which would be 2 to the third power, and that's dimension 3. But that's not the whole story. There can be objects that contains not 2 to the integral power if we double the size of the object. Like the Sempliskin triangle. Take a look at this. We can take a triangle and take the triangle in the middle and keep repeating it. And we get a figure that if we double the size of this triangle, we get 3 times the mass, 3 copies of itself, which would be a dimension that it's 1.58. It's plus than 1 and less than 2. We could imagine that it has so many points to line on a one-dimensional line, but still doesn't fill a whole surface. There's still some voids in here, so the dimension would be in between. A little bit closer to 2 dimensions than 1 dimension. And that's what we call a similarity dimension. We could define different dimensions, like that's not the only definition. That's what we will call mathematical fractals. They differ from regular Euclidean objects because they can be generated by simple functions, like the 2-sphere function that we all have learned at some point. It's a simple function that can describe a sphere. Fractals, instead, are generated by iterated functions. There are a set of functions that involves reduction, rotations, translations, and everything. And they get an input, and they generate an output. And the output it's an input for the next step. And they generate, like you can see here, the snowflake. It's in every iteration, it has a new figure. And at some point, you get a figure that has structure. No matter how small part you see, it still has a structure. And it will have a infinite perimeter. And there's no derivative at any point. So it's, for many times, that was seen like a mathematical monster. But yeah, we have tools now to analyze it. Some mathematical fractals have the properties of self-similarity, which will be, no matter how much you zoom in, you still get the same shape, and the small part resembles the whole. That self-similarity can be exact, which means that you can keep doing it, and you still get the same figure. Or it can be statistical or approximate, which means that it will resemble the whole at some points, but in other points, it would just break down or something. So now let's talk about nature, how these properties can be found around us. Those are pictures that I took in the park. these are rocks. You can tell by this, the size of the rock. If it's a scary or if it's a small rock. This cloud, you can tell if you're close enough to the cloud, if it's a bit of the cloud of the whole cloud. If that's just a piece of a tree or a whole tree, and as like the fern, like this tiny leaf, resembles the whole leaf, and the vessels on a leaf. And there are other things in nature that I couldn't find in the park, but maybe if I were to the winter, which would be shoreline, pineapple, which is a Brazilian fruit, so I wanted to show. The broccoli, Romanesco, in some animals, and lightning. And as well, in our bodies, in our blood vessels, in our lungs, in the brain. That's my hand in the max, but let's not go too far. That would be too much. And the mathematical fractals can be quite resemble nature, much more than Euclidean objects. That's the barnleaf fern. It's a set of 4 functions that generates a leaf that's quite look like a natural one. That's a link that if I have time I'll show later. And then I could get some conclusion that nature seems to prefer fractal geometry than regular Euclidean geometry. And self-similarity, while in mathematical fractals they can be exact, they have to break down at some point in natural occurring objects before the atomic scale, because we have to have atomic scale. It always looks like the same. And if you look around us, we'll find a big amount of fractals in anywhere. And I would like to say a phrase, a sentence that is in the introduction of the Barnsley book, Fractals Everywhere. Fractal geometry will make you see everything differently. There's a danger in reading further. You risk the loss of your childhood vision of clouds, forests, flowers, galaxies, leaves, feathers, rocks, mountains, torrents of water, carpet, bricks, and much else beside. Never again will your interpretation of these things quite be the same. So that will be it. Fractals are everywhere. And thank you very much. I think I have no time left. Yes. Where is it? After? Yeah. This generates the fern, and we can here control some parameters, like the angle. And the shift and everything else, and those are the functions that generate this pattern, as you can see here. So, anybody questions? Can we do 4 colors? Sure. Oh, it has the triangle also. Yeah. Oh, this rectangle tells what maps in what. They have the more questions?
So you said that fractals come from iterated functions, right?
Yes.
If I remember correctly, in complex analysis, there's something called a Mandelbrot set.
Yes.
It has also
it has a function.
But it's also a fractal. So I'm not sure if it's necessary that because it's iterated fractals.
Oh, you said the Mandelbrot fractals are generated by what?
What do you mean by iterated function?
the function that has an input and it spits an output, and then the output gets iterated many times.
Mandelbrot said this because I mean it's not defined like that. Is it? Is it? Okay, I'll have to look.
Yeah.
Is it?
Yeah.
Okay.
You mentioned two concepts. One is self-similarity, and the other is, well, non-trivial fractal dimension.
Yes.
What's the connection between those two concepts? One of them, does it require another?
Oh, I told here about the similarity dimension, which only works for objects that has self-similarity. If you imagine the objects that I showed here, they have also self-similarity. They are not fractals, but they have. But you can find fractals that don't have self-similarity. And then you would have to define another kind of dimension. That's box dimension that you'd have to. Could I write somewhere?
Yeah, there's some chalk there.
That's not chalk.
There's some chalk over there in the corner. Sorry.
Okay. If you had an object, that's this box dimension. You can it has a probability of taking off a square here. Taking off. So I would need here, if I have a scale epsilon, I would have here to have 8 squares to cover the square, the whole square, because this one is out. So I had 8 of the scale epsilon. For the next step, if I do the same thing here and randomly take off another square, I will be taking another whole square, which that would be only, and I would need 8 times 8 of the size epsilon over 3, and I would need 64. I'm trying to say, I'm not sure if I'm making this very understandable, but we could define a new dimension, but they would always have to involve the scale you were talking about. It always depends on the scale epsilon you were taking, and in the limits you have the epsilon goes to 0, then you have a dimension, and it should be they should match if you're if you're applying the same procedure, different procedure for the same stuff. And if they are not self-similar, you can define another dimensions, but they would have to be fractal also. There's this box dimension that you cover with box and counts how many boxes you would need to cover the figure. Like, suppose you have an object like this. I want to see what's the dimension I would have here. Then I choose a box of scale A, epsilon, and I count how many I would need to cover. And then I change the scale, the length of the box, and count again, and see how this scales with the size here, scales with the dimension, scales with the size of the box, and then I'll have the dimension, and it will be a fractal also.
It's a little bit like what you do when you calculate the length of the shoreline.
Yes, it depends on the size of a ruler.
Yeah, exactly.
Yeah, all fractals have this property. Thank you.